going to function properly. It's just been slow. I know I've got a fan issue with this, but that shouldn't affect its speed. It's just whoever had this before me, like the inside of this computer is filthy. It needs to be, I don't know if a can of air would do enough for it. Did anybody need a paper version that did not pick it up? Yeah, there's just a paper version of it. It seems like most people prefer it. You just have to hope that, the little school doesn't get shut down, or I don't get quarantined with my kid, or all that fun stuff.
You said I talked in quarantine.
You what?
You said I talked in quarantine.
Just listen to talk.
No, you said I talked. Talking. Right.
It's not what gets you quarantined. Cough. It's not what.
Stay away from me.
It's honestly the thing that you don't want to think for talking. You do. You do want to say you have to go and get tested. It's coughing is not by itself like indicative of it. The big thing is fever, honestly.
I just don't want to.
Y'all, stop it. We are going to the next 3 lessons. We're going to take the bulk of the 3. We guys have gotten used to much shorter ones recently. Why does it say it's 0 degrees Fahrenheit?
Yes.
Hold on here. Hold on.
That's good.
No, that's literally like 30 degrees below freezing. Oh, let me get it up to 70. It said on 0 degrees. I was like, no, mine's not. Mine's really warm. I don't know what's going on. Okay. Let me put my lid back on here and get my stuff out of the way. Now I have to, all these rock kits that this district has, none of them have their identification cards. So I'm having to literally go with my identification guide and manually ID these things, and it takes forever. So yay, since that's what we're doing, that's what I get to do for a while here now. And that will make it any bigger. All right, and I don't see a Smart Ink tab on here at all. So good thing I've actually put most of this directly into an animation. Your opener, if I go into it, today is the 11th. And I'll go through and double check and tell people if they had not turned some stuff in. All right, so it says, so far we've only looked at ionic compounds. We have. We've looked at making ions. And when ions make a compound, it's an ionic compound. It's not very inventive. It's what they're called. Your nonmetals, the ones on the left, I'm sorry, your nonmetals, the ones on the right, those normally gain electrons. They steal electrons. They steal them from the metals who lose their electrons. They literally take them off and they steal them. And then if they steal electrons, then they become negative. And the poor metals that have had their electrons stolen become positive. And however many they gain or lose is plus or minus that much. That's what we've done the last few days. There's a couple other major types of compounds, but the big one, they're called covalent. We haven't quite done that yet. And they don't steal electrons from each other. They share electrons with each other. So we've got the ionics where they literally steal them. And then we have covalents where they're shared. It counts for both elements that are sharing the same electron. So which do you think would be a stronger bond and why? I'm going to let you guys answer this one the way that you think, because we have not gotten into which is a stronger bond yet. We have primarily talked about ionics. And like I said, your nonmetals literally pluck the electrons off of the metal. They steal them. They gain a negative charge, and the metals gain a positive charge. Remember, you don't gain or lose protons. You gain or lose electrons. Covalents, which we're going to start at Friday, they share electrons with each other, and that electron actually counts for both atoms that are sharing the same electron. This is a tell me why you think, which one, and why do you think it's that way? Because we haven't gotten into the other type yet. And then if I go clicking through here, and I know they can't see my Canvas page, y'all can. Then we've got notes 22, which I've printed out. And then the assignment, it's not really a Google form. I changed it into a Canvas quiz. Just I better have. Shuffle, yes, edit, questions. Yeah, I turned it into a Canvas quiz because the Google form wasn't working right. So I just redid it. So absolutely everything is in Canvas today. Everything is in Canvas unless if you just pick a paper copy up. Okay, so, huh? Which is, I'm sorry, which is which? Well, maybe if we get through enough of this, then you can go back and answer it and be 100% right. This is why you don't know all the answers yet. I'm curious if your processing skills can figure it out without me blatantly telling you the answer. We are talking about the major types of bonds. Now, the primary two are ionic and covalent. Okay, but there's also what's called a metallic bond. This is why metals behave certain ways. But the big two that we talk about the entire year are ionic bonds and covalent bonds. So the one that we don't talk about a lot first, metallics. You've got your positive metallic cations because metals lose electrons to become positively charged. And they have the extra electrons are sort of floating around between the positive atoms that make up whatever the metal is that you're looking at. And they actually act like a cushion in between your positive metallic ions. Now, I hope you guys have played with magnets before. If you haven't, I am so sorry. But when you put lights, if we put a positive and a positive next to each other, are they going to push away or are they going to attract if they're lights?
Oh, wait, no.
No, lights. But do lights attract or repel? They push away. They push away. So you have all these positive ions that are wanting to push away from each other, but they don't because they're cushioned by electrons that can move in between them. It's not like a liquid, but we do call it a sea of electrons. They can move around these positive ions and keep them from literally pushing away and trying to explode, which would break the metal. You should know by now that if you throw a chunk of metal at somebody else in the head, it's going to hurt them. It's not just going to go and splat. And that's because of this sea of electrons. We can mold metal. We can turn it into wire. I'm trying to underline the stuff you're supposed to fill in to make it a little bit easier. So examples, what's the matter? I'm not, because it's not loading. Okay, I know. I'm sorry if the Wi-Fi is acting crazy. I'm not in control of the bandwidth here. Okay, but we have a couple of examples of either pure metals or alloys. Pure metal is going to be an element, so things like copper, gold, aluminum, ones that's not listed here, silver. Mercury is the only liquid metal, but it's still a metal. Platinum.
You have mercury?
No, it is actually illegal to have mercury in classrooms since like 15 years ago. No, 15 years ago because it's toxic and it'll make you go insane before it kills you.
I was wondering.
That's why they called the Mad Hatter in Alice in Wonderland, because to make felt, to make hats, you used a mercury compound, mixed it in with animal fur, and it turned it into felt. So they touched it and they literally went cuckoo before they died, which is why it's called the Mad Hatter. That's why he was nuts.
I was wondering. Oh my God, I got mercury on it.
So
back in 2003, that's when it was illegal?
no, let's see. It was my first district I worked at, and it wasn't IPC, so it was at least 2007 when I started teaching chemistry at that school. We had to go through, and OSHA said if you have any mercury at all at mercury thermometers and stuff like that, that has to be disposed of properly. So you're not going to have mercury, I mean, maybe in college, but not in high school.
That was 11 years ago.
Yeah. I said I thought it was 15, then I realized I haven't been teaching that long, so at least 10. I don't remember the specific year, but I remember going through our stats and having to get rid of all of the mercury. And I found a jar of mercury that was just open, and it had coins floating on its surface because mercury is so dense. I said, oh, that's just awesome. And we had to get rid of that. Anyways, alloys are mixtures of different pure metals. So examples of alloys would be brass, bronze. There's tons of them. Tons and tons and tons of alloys. So, and I can let me pick up a paper so that I make sure that I did underline everything. Because I did this on Sunday and I was really tired. So your sea of electrons. Let's see here. Why are metals good conductors of electricity? Okay, it's called the sea of electrons. You guys have this image, and I know it's on your notes. It's on the actual page. It looks like a bunch of little balls. Well, the larger ones are the metal ions, which are positive. This is silver. And then the little balls in there are the little electrons that are cushioning those positive, in this case, silver ions. And it keeps them from trying to push away from each other. Now, when it comes to electricity, because I taught physics and I used to teach my kids how to splice wire and like create circuits and whatnot, the electricity actually does not go inside the strand of wire. And you should know that there's insulation on the outside. Okay, so you don't electrocute yourself. Okay, but if you've ever, I mean, don't do it to your computer cable, but if you've ever cut one of these and you look inside it, you see different strands of copper. It's not one big wire, it's a bunch of little strands of copper. Well, you may have extra insulation. Well, that's not good if you can see the exposed wire. But the electrons, the reason why we use stranded copper is there's more surface area and more electrons can go along the surface of those strands. It doesn't actually burrow inside the wire. They dance along the surface. That's how electricity works. I love doing electricity because I could shock my students every year and not get in trouble. It was amazing. And they'd be like, is that going to hurt? And I'm like, yes. And they would go, ow. And they're like, I'm going to do it again. And I would just watch them shock themselves for 10 minutes straight. The boys would do it much more than the girls. The girls would be like, I don't want to shock myself. Well, I don't have, I mean, if we have Van de Graaffs and wind search machines, I don't have them in there. I don't own one personally. So ductility, if it is ductile, we can turn it into a wire. We do this with copper for regular old electrical components. Your cell phones, they like to use silver. That's actually why there's a silver shortage right now, because everybody has at least one cell phone. In space, we use gold because gold doesn't oxidize. But we can turn these metals into wires, which is called ductility, or they are ductile. We can hammer them into thin sheets, which is malleability, or it is malleable. That's how we get aluminum foil. The aluminum is beaten into a thin sheet. We do the same thing with gold. But the sea of electrons, and I think you have this one to the left of your picture, it allows the electrons to be flexible, not stretchy, not like elastic, but it allows them to be flexible and they move where they are needed to keep the metal from breaking apart, which is why we can do these two things. Otherwise, it would snap. All right. This is the picture that you guys have. And it isn't on your thing. You're welcome to add that if you want to. It gives the metal the ability to be molded, not stretchy flexible. You can change its shape and it doesn't just shatter. I know mercury is different because it's a liquid. So don't think of a rubber band. Don't think of a trampoline. That's different. So you can manipulate the metal, which I don't have any that I could actually do that to that are in my collection, because these are all minerals and rocks. Where most of them, if I hit them with a hammer, they would break, which we will do to the geodes when we get to this section.
You should tell us, like us?
No, our space kits. These are hollow inside. Well, some of them, that one feels hollow. Where if you hit it just right with a hammer, it'll break, and then you can see the crystals that are inside. It's volcanic rock. It's called igneous rock. Gems that are made from lava and, in this case, lava that has cooled down. They're all like, I don't want to learn about rocks. I said, rocks can actually be pretty and interesting. I will bring my specimens from home. All right, ionic bonds. This is what we're focused on first. This is what we've been talking about. You have a positive ion, which is a cation, which is normally a metal that has lost electrons. You have a negative ion, which is normally a nonmetal that gains electrons. The nonmetal steals the electron from the metal. It takes it from it. In the case of salt, sodium chloride, the sodium is the metal. It will lose its Na+1, so it loses one electron, has one valence electron. Chlorine has 7, and it wants to gain that one electron to get up to 8, which is going to give it a -1 charge. With charges, opposites attract, and your slightly positive sodium charge is attracted to your positive chlorine or your negative chlorine charge, and like a magnet, they stick to each other. If you put salt in water, it dissolves. Ionic bonds are actually the weaker of the two. It makes the harder substance normally, but you can break apart ionic compounds simply by just putting it in water. Not all ionic compounds are that way, but a lot of them are. The magnetic attraction in chemistry, it's not magnets, it's still a magnetic attraction. We call it an electrostatic force from the motion of electrons. They stick to each other like static electricity. Do I have a balloon over there? I bet you do. Let me find my wool. There's no wool.
Wool?
Wool. Sheep's wool. Why would I have a wolf?
You could have stuffed wool.
I just gotta figure out where it is.
Yeah, you can.
That would be smart to have a real wolf up here. Yes, that
You can
would be.
train
Here we
them.
go. There's some right there.
That's something called training.
They're wild animals.
So,
People that try to make wolves as pets get bit.
that's why I'm gonna own a hyena.
A hyena, because that sounds a lot safer than a wolf. A hyena.
Sure does.
No,
Hyenas are awesome.
I don't want to. They will never show.
You put it on front.
They can't see what I'm doing.
You can't.
Y'all should have this. We're trying to make your notes shorter on you by giving you so much of it filled out already. So this top image, which you guys have, is showing the sodium and the chlorine. That one outside valence electron of sodium, I'm gonna get this balloon tied off so it doesn't fly around the room and spread my breath all over the room. Oh, come on, go through that. Okay. Okay, so, because they can't see it online. So this is sodium's one valence electron. And what it's going to do is it's going to be moved completely over to chlorine. So now we're missing that electron that's on this dotted line. It becomes +1 because it lost one electron. Chlorine now has an extra one than it did before, so it has a -1 charge. This is the magnetic attraction between the two. When you have an ionic compound that makes its thing like salt does, salt crystals look the same. Now, if it's being shaken out of a salt shaker, they're little. But if you take salt and you mix it in with a glass of water and you just let it dissolve, those crystals get huge. But it's just a bigger version of the little one from the salt shaker. They form specific structures, crystalline structures, and they always form a certain way. Sugar is the same way. Itty bitty bit of sugar is the exact same shape as the sugar cube. It has a specific structure, although sugar is not ionic. Sugar is covalent. Okay, so you watch this balloon's gonna pop, and I'm gonna go, ah! No, it's not in my hand. Okay, so I don't know. It's at least it was cold this morning. It's not raining. It should work. So all I'm doing, if you guys can't see it online, all I'm doing is rubbing some sheep's wool on a balloon because I don't want to use my head. And I'm transferring electrons from one to the other, just like these things do. And what's happening is the electrons are going from the wool to the balloon, which means that I can hear it. Good, you should stay. That the wool is now a little bit positive because it gave its electrons to the balloon. I bet you it's not going to stick to this.
Just throw it up.
That changed the thing. Okay, so, and the reason why the balloon sticks is because the balloon is more negative than the wall. The wall is neutral, but the wall is still more positive. It's marked. The wall is still more positive than the balloon, and so you have that magnetic attraction. That is exactly what these things do, which is why an ionic bond is weaker than a covalent bond. No, it's gonna get sucked over to that rock and pop, so I'm gonna put it in the chair. No, because I have another chemistry class. And I think I only have that one balloon. I'm not joking. I don't think I have any more balloons. I don't teach physics anymore, so we use balloons all the time in physics. I can make pieces of paper fly all over the room with balloons and all different kinds of stuff. So it's the same concept as that. I'll show you in a bit if you have time. Okay, so ionic compound characteristics. They are mostly crystalline structures. I think this would be next to that lattice if you're going to put these in here. They have high melting points. I may not have added this on here. You do need to know this part. Looks like I did not add this one. Oh, no, here it is. It's on the back. I apologize. Most are crystal structures, lattice. They form a specific pattern. They have very high melting points. Covalent compounds don't. You have a very strong magnetic attraction, but if you put a lot of ionics in water, because water's polar, we'll talk about polar compounds next week, the water can pull them apart. The polarity of the water, because water has a positive and a negative reason also. We haven't done structure of molecules yet. That will be Friday. But the way that water's arranged, the two hydrogens around the oxygen, water has a slightly positive part and a slightly negative part. And those different sections of water pull the ions away from each other. The water is stronger than the ionic attraction in the compound, which is the case of salt. And if something can dissolve in water, it's called soluble. If it cannot dissolve in a liquid, normally water, it is called insoluble. Why is it not going there? It looks like you guys have this one. I already gave it to you. So the water, when the water is stronger than the ionic compound, it will make that compound dissolve. It'll pop the ions off of each other. They'll still carry their positive and negative charge. They're just floating around in the water. They're not stuck to each other. If you can melt it and it will conduct electricity, then, well, it's not going to do it in the solid form. So you're not going to just like stick a chunk of salt down and it's going to conduct electricity, but salt water will. It's easier to get electrocuted with salt water on your skin than regular water on your skin. But it's easier to get electrocuted with water on your skin than if your skin is dry. Please don't test this out by sticking paper clips in the socket.
I want to do that.
No, I have had students do that before. I had a student stick scissors in the electric socket.
Is that sticking in the socket?
Don't stick a fork in the toaster when it's going.
Then stick their charger.
Yo.
I did it once just for fun. Did not feel good.
Oh, goodness.
Because you know those pins where you can put some gas inside to make a shot? You can like that for a little bit worse.
Oh my gosh, please don't electrocute yourself. All right, so aqueous solutions just means it's in water. That's what aqueous means. But a lot of ionic compounds that are dissolved into water will conduct electricity. A current will go through it much easier. Ionic compounds tend to be brittle, which means they're going to shatter if you hit them. Glass is a silicate. That is different.
What about ice?
No, ice is frozen. Well, water is a covalent compound.
It's still warm.
It's the frozen version.
Not like it.
It just has to do with the fact that it's a solid. It's not flexible. And now I'm not going to take hammers to these, at least not yet. the geodes eventually. I need to find the rest of all my samples and bring them up here. I think this is a little bit loose piece of it. I don't think it's gonna come out.
You can't break it.
I don't want to just break it. I want to slide it out so we can put back in. That's my good sample for fraction. Okay, the other type we've not done yet, covalent compounds, covalent bonds. They share the same electron between two different atoms. It counts for both. Now, I'm going to teach you how to do ionic Lewis dots tomorrow, which in my opinion is much, much, much easier than covalent compounds on Friday. And then we're going to be just working on these Lewis structures for both of them on Monday. And I know you guys are going to need a day where you can work on them and I can answer questions if you're confused.
Well, I need time to do Mr. E's.
I need to, oh shoot, let me go backwards. I apologize, let me go backwards. I know there's questions on it because, and I've had one person turn it in and Jimmy, no, it's not right. It was not right.
Jimmy wasn't the one to turn it in.
He did turn it in. I looked at it, but it was not done right.
No.
There are, okay, so you have to think of that Mr. E thing as a periodic table. So the people represent different atoms. Like up there.
Sorry.
Okay, and the periodic table is organized by trends. Like the things in group 1 all have one valence electron. That's why they're in group 1. Things in group 2 all have 2 valence electrons. You have to figure out how that translates to the stick figures. And like the big hints I gave you in class is look at the numbers of hair on their head. Look at how many fingers they're holding out. How many arms are being held out. The pattern of their clothes and how big they are. Because they should have the same trends as you're going both down and across. It is the periodic table, just cut out the transition metals. And then smush like the first 3 rows over to boron and aluminum. This is an example of a covalent bond. So both of these are nonmetals. Covalent compounds are made up of nothing but nonmetals. There are no metals in a covalent compound, ever. They are nonmetals. These are both fluorine atoms. Fluorine has 7 valence electrons. Now it doesn't like pop one off over here and then pop one off over there because then they both still have 7. So what they do is you're sharing, this one came from the one on the right, and this one came on the one from the left. So this has originally had 7, but if it's sharing this one, then the one on the left has 8. This guy had 7, but it's sharing this one, so now it has 8. And they both are now obeying the octet rule because they're sharing their electrons equally and they make much, much stronger bonds. They don't make lattice crystal structures. They form what's called a molecule. Ionic compounds don't make molecules. They make what are called formula units. We'll get back, don't worry. You'll have to know that for right now. We'll get back into that. Covalent compounds don't make formula units. They make molecules, which are made up of different atoms. In this case, they're both the same element, which is fluorine, but it's made up of more than one atom to make a molecule. This is fluorine gas. Well, actually, let me take a look. No, actually, that's water. The blue one is oxygen, and the little yellow ones are hydrogen. These are water molecules, is what this is representing. But they're not lined up like in brickwork, like the ionic ones were. Okay, so properties of these guys. They are only made up of nonmetals. The way that you tell them apart, and I know I'm sorry online, you can't see my draw erase board, but I'm not even going to try to draw on the smart board. So this is a formula unit. This is a molecule. If the first thing you see is a metal, which sodium is a metal, this is an ionic compound. If the first thing that you see is a nonmetal, which hydrogen is a nonmetal, then this is a covalent compound. This is a molecule. With this one, chlorine took sodium's 1 electron. This became -1 and this became +1. With these, each hydrogen is sharing its electron with an oxygen. So then each hydrogen has 2 and the oxygen has 8. They can be solid, liquid, they can be gas at room temperature. Ionic compounds are almost always solids at room temperature. They are based on how heavy they are by their weight. Very, very low melting points. Ionic compounds have very high melting points. So to get water to go from ice to water, that's at 32 degrees. That is a low melting point. I don't even know what the melting point is of salt. I'd have to look it up, but it's a heck of a lot higher than freezing. Mhm. You can melt anything if it's so hot at temperature. Honestly, anything. Melt rock into magma and lava. Gotta get hot enough. And at one point in time, our planet was nothing but a giant molten mass. The volcanoes spit all the stuff out from inside. And then we got an atmosphere. And then we got bacteria. And then we got water. Actually, we got water first. And then we got bacteria. We're in the process of doing that in our space. We're not at evolution yet, but we've been talking about how the Earth has changed from 4.57 billion years ago to now. In order to melt the covalent compounds, it's not a magnetic attraction. They're sharing. You just have, not the bond itself, you have to interrupt what are called intermolecular forces. The bond itself is very strong. The intermolecular force is not. You don't have to necessarily break it, it just has to be overcome. They do not conduct electricity well. Ionic compounds do. The reason why they don't conduct electricity like the ionics do, the ionics are going to turn into positive and negative versions. These don't. I can't remember.
I have a question.
Yes.
For tomorrow, can you just like work on the assignment or the state assignment all day?
No, that's why I have that one open all the way through Friday. I'm telling you, you have to find the trends. Yeah, it took me a little while to figure it out myself until I realized, oh, that's what that means.
Can you like at least show us at least how to do it too?
There's 2 of them that are already in the right spot. We'll have to see how much time we have. So anyways, if there are no separation of charges in a molecular compound or a covalent compound, these words are interchangeable, the electricity is not going to go through it. Do you have this one on here? 4 conductors with electricity in any state. Okay. Now that's the end of this one. So let me turn the light back. Okay, so this Mr. E thing. Now I'm not going to just do it for you. I need to share the way that my screen, let me move my screen. Get this back to the right slide. We have 10 minutes, so I have enough time to go over it. Now there is well, actually, let me, before I get into that. Oh, I see Alexis and Veronica. Okay, I'm going to share my screen. Okay, you guys should be able to do this without, because it's just multiple choice questions. Now the question is, did I give you multiple attempts? I'm going to change it. Let you have to, in case you totally mess up on it. Okay, now on this Mr. E, if I find it, nope. Chemistry, not that one. Let's go. We are in what, the third 6 weeks? Oh, did I really do it on? I gotta figure out where I put it. I bet you it is in on my Earth space. I accidentally saved the stuff with my Gmail drive, like my personal one, instead of the schools, and so it may be on my other drive. Okay, so if I open this guy up, that's what happens when I have like 50 tabs open at the top. I can't pay attention to it. Oh, that's not the one I'm looking for. That was copy of student. I want the original. Let me go into my, yes.
Well, you said it was definitely one that would have a medal. Like the first one you know.
You know what? Somebody did. Is that what they were talking about in the other? Somebody did. It's like not letting you. Or is it already finished on yours? Why did it do that?
Yeah.
I don't know if it's right. Hold on here. Wait. That's they were talking about that in the email that they were, but I made my own copy. Hold on here. I have to go into my other drive. See, this is, well, if it's I don't know if it's done right here. I don't know why I can't find it in my drive. But that's mine. I don't know if it's right. Hold on. I gotta figure out where it went. I don't know where the heck it went. Okay, well, I'm just gonna go back into here. All right, so.
Oh my God, I've been talking about it.
Okay, well, okay, so I have no idea. Okay, so these. I don't know if it's right. Okay. Oh, wait. That guy was in the right spot. Well, heck. Okay, so these were the two that were given to you. Although now I have no idea why it has to have been the way that Miss Castleberry sent out the original that I don't know. Okay, so this would be group 1, right? And then group 2, group 3, and 4, and 5, and 6, and 7, and 8. Those just like the periodic table. So you're look. I told you guys, look at how many hairs are on their head. Look at how many fingers they're sticking up. Look at how many arms they have. Look at their clothes. What's the pattern on their body, and how big they are. So what's representing the group number then? Yes. And what's representing how many electrons they have? And what period are they in? No, not their size. No. Something else. So you look at something else besides their size. Their arms. And as you go down the periodic table, what happens to the size of a radius? But it looks like it's already been completed for you, and I can't go back and figure out how to fix it.
So you just turn it in?
I guess so. Okay, but well, I don't understand why Jimmy's. I don't understand. I don't understand because I made my own. It wasn't like that. I don't understand why it did it. I mean, I'm still, like I said, I have never used Canvas before this year, so I'm still figuring. I don't understand, and I also don't understand why I can't find it in. Here, let me open. Let's try Mr. E. Copy of student. See, this is the original student file right here. So if I go in here, see, and it should not be done. This is the original file. But it shouldn't be filled in. I have no idea if all the other stuff was done.
We only got 3 more minutes.
I know, but I'm gonna stop the recording here real quick. I'm gonna stop that. And I need to get